All right, so we're back in the second quarter. And we started off talking about motor units, and we talked about this chart. So we're jumping in on page 91. And here's what we need to understand. Motor units operate off of this fundamental theory called the size principle. What's it called?
Size.
What's it called?
Size.
What's it called?
Size.
Now, there's a great picture of size principle down here on page 91 in the bottom right left-hand corner. Now, does anyone remember what the philosophy of all or none talked about? Do you remember? Can you go for it?
You either recruit all your motor units or none of them.
You either recruit, so your brain sends a signal to go over there and pick up that cup of tea. Here's the whole thing. Did my large motor units get recruited just as much as my little ones did initially, all or none, to make the magic happen? Yes. So everything gets recruited, all or none. However, something cool starts to happen with this thing called the size principle. And if you'll look, the little green dots are motor units that are low in their recruitment order and low in force production. So they're way down over here. That would be, you remember the example when I talked about being able to pick up the pen and put it down, pick up the pen and put it down, pick up the pen? These are low in the recruiting order and they're low in force production. Now, here's what starts to happen. As our body is needing more and more and more motor units to get bigger and bigger and bigger things done, there's this thing called selective recruitment. So what selective recruitment does is it allows me to, my brain is all of a sudden saying, hey, you're going to go over there and pick up that desk. So what it does, it lets me all of a sudden go through the one that I don't need for the pen, the ones that I don't need for the cup, and then they allow me to come right here and get to these bigger ones. So again, think about it like this. These are the ones that allow you to pick up the pen. These ones in the middle are the ones that would allow you to pick up the cup. And these giant ones here are the ones that would allow you or anyone to go. And this applies to all sports, not just table picking up, right? Right? Yes, laugh. Okay. So, yeah, there's the, I love that when you do that, Walker. Okay, so here we see the thing of size principle. They're always recruited in order, except when there's a big job. You know what, here's the whole thing. If you needed to demolish a building, could you demolish an entire big building with one stick of dynamite? No, you need to all of a sudden have dynamite wired throughout the entire thing so that when you create the boom, the magic actually takes place. So what is that called when higher motor units skip in front of the other ones to make the magic happen?
Selective recruitment.
What's it called?
Selective.
What's it called? Selective recruitment. Because guess what? Your body will respond to whatever you ask it to. So here's what's happening. Your central cortex in your brain is saying, that's going to be heavy. We don't really need these. They're going to act as a support system. You need to bring on these larger muscles to make the magic happen. Typically, larger muscles have larger motor units. Tell me that makes perfect sense. Yes, very good. So in this box in the right-hand column, we see that with heavy resistance training, all muscle fibers get larger because motor units are recruited in a sequential order by their size to produce high levels of force. In advanced lifters, that would be all of you. Remember, we're all advanced lifters. If you're not, you're going to be in the next 6 weeks. Okay? All advanced lifters, the central nervous system adapts. Your body will respond to?
Whatever you ask it to.
By allowing well-trained athlete to recruit some motor units in non-consecutive order by recruiting the larger ones first to create the greater production of power and speed in movement. It's this magical thing. Now, does this happen in untrained individuals? No. What does it happen in? Trained individuals. Friends, You have got to get trained and you have got to stay trained. You have got to do what? Get trained and stay trained. I'm about to give you some numbers here that if you're not a trained human, you're going to realize what you're really giving away by not training regularly. So jump over on page 92 with me. And guess what? You already know this. This is the second or third or fourth mention of this thing called the NMJ. What is the NMJ?
Neuromuscular junction.
What does the neuromuscular junction do? It's the space between what and what? Space between the motor unit and the muscle. Now, here's what we need to understand. In untrained, let's just say this is the motor unit, and let's just say this is the muscle. Now, what we need to understand is, in untrained individuals, it takes this motor unit longer to get to the muscle. Does that make you more powerful or allow you to have more speed? Yes or no? No. In trained individuals, it's almost like an impulse where you can have the signal sent to the muscle and it instantly reacts. That's when we start to see motor efficiency coming into play. Your body will respond to whatever you ask it to. So if you're consistently asking your body to be able to create more force, create more power, create more speed, it's because the nervous system has adapted to sending the signal across what?
Neuromuscular junction.
The neuromuscular junction. So all of a sudden, this now becomes this river, that's why I drew it like that all of a sudden is super easy for you to powerfully go across. You know, people that are untrained, they'll stand there and that's like, they'll look at it going, ooh, I don't know if I can make that or not. People that are trained, before you know it, they're there. So how your body responds is what you're asking it to do on a daily basis. And that's the exact same flip as what I typically make you say all the time. So if you want to stay slow, stay slow. Because remember, your body will respond to whatever you ask it to. If you want to get faster, then you got to make the time that this impulse gets delivered to the muscle. Because friends, the muscle can't do anything until it's received the impulse. The muscle's just hanging out. Every single muscle. You guys, remember that our friends that are in the lab over here that have had different issues with strokes, have had different things going on, and they look at that poor muscle and they're trying to visually kind of make it work, but the central nervous system has had damage somewhere along the way. So we see them not being able to jump the river. We see them having those chronic problems instead of being able to speed this up. Now, we know even with people that have had strokes in the lab, we know that their body will adapt to training, and it might not ever be lightning quick, but it can be quicker. It can be quicker with adaptation processes going in play. So now, there's another thing that happens in your body. It's called neuromuscular reflex potentiation. It's a big vocab word today, potentiation. What do you think potentiation means? Lots of potential for things to happen. Now, there is this thing called your myotactic reflex. This harnesses, I love that word, it harnesses the involuntary elastic properties of muscle and connective tissue that acts positively to increase force without adding energy. So what we need to understand is, if we could tap in to this myotactic reflex and move towards this thing called muscle potentiation, we could increase force really without having to do more effort or more work. It's a beautiful thing. Now, the main place that we see this being measured is where your soleus plugs into your Achilles tendon. Now, what does your soleus and your Achilles tendon allow you to powerfully do? Starts with a P. Plantar flex. Now, here's what we know is the better we can have people be more efficient and effective at plantar flexion, the more power they can produce. And we see this even starting with a deadlift, even starting with a power clean, even starting with a vertical jump. We can change this as it relates to this myotactic reflex. I also like to think of it as, tell the truth, as a kid, how many of you in here had a slingshot ever? Do you have a slingshot? Okay, so the myotactic reflex is basically, and we got them for our boys for Christmas. They're the whole thing, they're the wrist rockets, the ones that are like on steroids. So you hold your wrist rocket here, and then all of a sudden you pull this back. And here's what we know. The more I pull this back, the more energy I am loading in that rubber band or in that elastic tubing. It's creating more energy. Now here's also what I can tell you. I don't have to deliver a lot of force here to pull that force back another inch. Well, when you're thinking about how much farther that rock is going to go, simply pulling from here to here, would that make a huge difference out there? Yes. So I didn't have to use a lot more energy here. Same thing, if we will train, friends, you got to be doing plyometric work. If you're not doing plyometric work, you are not tapping into this myotactic reflex. You're not increasing your potential to increase force. Because here's the question before the buzzer goes off for halftime. What sport doesn't involve some sort of forceful plantar flexion?
Bowling.
Bowling. Now if
Billiards. Oh, that one where you...
billiards. That might be the only answer possible. Well played, my friend.
That one that you ski and lay down to shoot.
But I had to ski to get there. True? So I think what we realized is in the realm of sport performance athletics, the ability to plantar flex is highly important. True or false? True. So if this is something that we can increase the potential without doing a ton of extra training, why wouldn't we do it? All right, there's the buzzer. Nice job. See you in the next session. Stand up again.